So we've already completed part one of the portfolio, bacteria growth, and we derived the exponential model formula. Now we're going to look in more detail at that growth factor, the B letter that we had there in the formula. And we're going to examine what happens when you vary that a little bit. So we're going to examine in the context of something called exponential growth and exponential decay. Okay, I'd like you to do something with me a little bit of an exercise. I'm just going to bring up my calculator here, my Windows calculator. It's scientific right now, and we're just going to change it to standard. So all we need is a 4-function calculator here. And I'm just going to start with 1, and we're going to multiply by 1. 1 times 1, as you know, is 1. And every time I hit enter, it multiplies by 1 again. Notice the amount is not growing. It's not shrinking. It's not getting smaller. It's not getting bigger either. It's not changing. Okay? So there's something about 1. 1 is kind of the dividing line. When we raise 1 to a power, nothing happens, right? When we raise 1 to a power. Now let's try something a little bit bigger than 1. 1.01. Okay? So let's actually clear that here. I'm going to start with 1. I'm going to do 1 times 1.01. And when I do, I get 1.01. But when I multiply that by 1.01, I get 1.0201. And I'm going to keep hitting enter, and the calculator is going to keep multiplying by 1.01 every time, repeatedly multiplying by 1.01. You notice the quantity, and I'm going to get faster here, is growing. It's getting bigger. We're almost up to 2. In fact, here we go. Boy, got to really click. Oh, there we are. We're up to 2. Okay. And if I can fast forward this video even faster, you can see that it grows, and it actually starts growing faster. We're already up to 3. All right. And theoretically, this is going to grow without bound. It's going to grow infinitely large. Okay. So the 1.01 is bigger than 1. When we multiply by a number bigger than 1, the quantity gets larger. Okay, let's do the opposite now. Let's take 1 times something a little less than 0.01. I'm going to say 0.0 or 0.09. Okay, 1 times 0.99. So just 100th less than 1. And hit equals. Now you'll notice here as I multiply repeatedly, the quantity is not getting bigger. We're down to 0.8 now. The quantity is actually getting smaller. So when I multiply by a decimal that's less than 1, my quantity gets smaller. So when my growth factor is bigger than 1, that represents exponential growth. When my growth factor is less than 1, that represents exponential decay, shrinking, getting smaller instead of getting bigger. Okay, so here's a scenario. This is task 2. So head your paper, task 2. Okay, now I'm going to give some numbers, use some numbers as examples. I want you to create your own numbers and do your own calculations. Okay, your numbers are going to be different than mine. There are 2 towns, Boomtown. Boomtown has a population of 100,000 people. A pretty good sized town. I think Boise is somewhere around 200,000 people. So it's a good sized town. Population 100,000. But it's decaying. Actually not decaying. Yes, it's decaying. It's decaying 4% every year. Every year they lose 4% of their population. Okay, we're going to model that. Now think about it. That means last year we had 100%. This year now we have 4% less than 100%. So here's how we work out the decay factor, the growth factor or decay factor. B is 100%, take away 4%, because it's decay, we're losing. What is 100% take away 4%? It's 96%. Now you're going to do the same calculation, but use a number other than 4%, maybe 5% or 3%, okay? So it's going to decrease by 4% every year. That means every year it's going to be 96% of what it was before. All right, so let's rewrite that as a decimal. 96%, you may recall, to change a percent into a decimal means to move the decimal 2 hops. So 96% is 0.96. And that's the growth factor in my formula. So my general formula, which we derived last time in task 1, is y equals ab to the x, where a is the start value, b is the growth factor or decay factor, so in this particular case, my formula for Boomtown becomes y equals the start value, 100,000, times the growth factor or decay factor, 0.96 to the power of x. Okay? And so Boomtown is going to be shrinking. In fact, I can model that on my standard 4-function calculator, which I seem to have closed. Okay, so let's open it here just to show you what it looks like. We have 100,000, and we're going to multiply by 0.96 repeatedly. After year 1, 9,600. I put in 10,000. Clear that. 100,000. There we go. Times 0.96 is 96,000, and so on. And you can see as I continue to click, we're down to 56,000. The population of Boomtown is decreasing. Okay. All right. That's Boomtown. Now let's bring up another town. I'm going to call this one Smallville. Okay. It's got a population of 10,000. Much smaller, 10 times smaller than Boomtown. Okay, but it's growing. It's got a growth rate of 4%. So here's how that works with the growth factor. It was 100%, and now the year that follows, it's 4% greater. 100% plus 4% is 104%. Okay, so as a decimal, move the decimal 2 places, that's 1.04. Notice that's a number bigger than 1, so this represents growth. And my formula for the population of Smallville is 10,000 times 1.04 to the power of x. Okay? So again, you're going to use a different starting population, use some other starting population, use some other growth factor, maybe 4% or 3%, okay? But you're going to create a formula for your Smallville, okay? So with your examples completed for this part, let's go on to the next part. The next part is in Desmos, okay? And I'm just going to type desmos.com/calculator in a window. And we're going to bring up our Desmos screen. We're going to enter the 2 formulas. Y equals 100,000 times 0.96 to the power of x. And y equals 10,000 and 1.04 to the power of x. And we're going to compare these 2 formulas. Okay. Now you'll notice I can't see anything because my scale only goes up to 6. Okay, so I'm going to click the wrench tool and I'm going to change the x-axis. The x-axis is going to go from 0. The x-axis represents years. So I'm going to measure out in years from 0 to 50. And my y-axis is population. So that's going to go from 0 population to 100,000. Okay, and there we go. And I'm going to scroll wheel out a little bit so we can zoom out and see what's going on. So as you can see, the population of Boomtown starts at 100,000. Population of Smallville starts at 10,000. Okay, the population of Boomtown is decreasing, while the population of Smallville is increasing. Now, as you can imagine, they're going to have the same population somewhere. So as I look down on my graph, I can find the point of intersection. And let's interpret this point of intersection. This point of intersection says that in 28.767 years, almost 29 years, but the population of both towns will be 30,903. Okay, so both towns will have a population of about 31,000 in about 29 years. Okay, so what I'd like you to do for your portfolio is take a screenshot of your Desmos graphing calculator screen for your numbers. Remember, you're not going to use 100,000, you're going to use some other number, some other big number. You're not going to use 10,000, you're going to use some other number that's smaller. You're not going to use 0.96, you're going to use some other decay factor. And you're not going to use 1.04, you're going to use some other decay factor. Okay? And I want you to answer the following questions. When will the population of the towns be the same? And if you can, when will the population of Smallville be twice as much as the population of Boomtown? You can estimate that by the graph. Here, in my case, it looks like 20,000 is reached by Boomtown in 40 years. And 40,000, 40, 50, almost 47,000. This is right here. This is 48,000. So it's before that. So when is the blue about double the red? I would say somewhere in here. Okay, so somewhere in a year about 32, 34, 36, 38, about 37 years or so, the population of Smallville will be twice as much as Boomtown. All right, hopefully that makes sense. Let me know if you have any questions.